There we go. All right, welcome to the IF04 parallel session. We have just a few slides for introduction and to introduce like what we expect to happen in the session today. So this is a quick reminder of what the instrumentation frontier 04 is. It's the trigger and data acquisition instrumentation frontier. TDAC systems being the systems that collect data at the front of detectors, reduce the volume of the data, and then summarize it into high-level quantities. So this is a very challenging area for the future because we face an enormous throughput of data, and we need to have high reliability also in extreme environments and accommodate fast timing and precise synchronization. So, oh yeah, the bolding is not relevant here, but this is our interests include the following: basically high-speed data links and transfers, real-time processing hardware, online processing and high-level trigger reconstruction algorithms, autonomous operation control and calibration of detector systems, and timing synchronization for triggering and event reconstruction. Okay, so that's basically what IF04 is, and these are the white papers that were submitted for IF04 with links to where they're located in archive. So you can see we have particle tracking and triggering, track-based triggers, fast machine learning, readout technologies for future detectors, and another paper that describes a lot of different innovations in trigger and data acquisition that will be helpful for the future and next generation facilities. Okay, so to go over in a little bit more detail, and you're going to see a lot more of these in the talks, what this section is about. First, fast machine learning in TDAC, where fast is like less than millisecond, often down to the microsecond level. It's useful in a lot of scientific domains. So, and many different kinds of detectors can benefit from implementations of fast machine learning. LHC detectors, neutrino detectors, dark matter detectors, EIC, gravitational wave, and so on. And I have a table here to kind of demonstrate like the speed required by a variety of different fields. And typically, oh wow, suddenly I can hear. Okay. All right, so typically this takes the role of fusing machine learning into hardware devices or even GPUs. All right, and then the next thing that we have talks on today is tracking triggers. So this idea is to have early stage triggers based on tracking information. This is challenging because reconstructing tracks and detectors is typically a very computationally expensive procedure. And there are a variety of different physics signatures in high energy particle physics and beyond that could make a lot of use of these kinds of tracking triggers. So hardware-based tracking has been explored and used in multiple previous detectors, and we'll see kind of a history of that later in the session. And there are multiple approaches to try and perform this tracking in the very short time allowed in early stage of triggers for particle physics experiments. And this below is just an example of tracking from a SNOMAS white paper using highly parallelized graph computing architecture implemented on FPGAs. All right, and then finally we have readout technologies. So improvements in readout technologies are necessary to handle the high data rate of future detectors. So this includes wireless communication to enable designs with localized readout and fast analysis and triggering. And you can see more justifications there, and also next generation rad hard links, because radiation hardness is also a major concern in a lot of particle detectors. And then at the bottom, we have linked again the readout technologies white paper for more information there. All right, and then for today's session then, these are kind of all of the topics that we're going to go over. The goal for today's session is to discuss and generate further feedback to refine the report, particularly what key messages we want to deliver for the IF Instrumentation Frontier Executive Summary. So you can see the executive summary of our report right there, where we mention machine learning in TDAC systems, design of TDAC architecture, and readout technologies. And the draft report is also linked here, so you can have a look. Please do provide any feedback that you have. This is still the first draft of the report that was sent around. So any comments can be collected in this Google Doc that we have set up just here. And finally, for today, this is our schedule for the session. One note is that we became aware that coffee is not available until 9:45 in Ken Hall. So the coffee break is going to be shifted to 9:45, which would be after Christian's talk, if that is okay with you, Christian, if he's connected. Okay. Okay, great. All right, and then another note is, has Sasha connected?
Sasha is here.
Is here, okay.
I am connected.
Oh, it's connected, okay. Not here physically, as you said that the door opened, so I was like, okay, so then we can proceed as planned, moving next to Sasha with his talk on readout technologies. I will stop
Thank you.
sharing.
You can share the slides or I can do that.
If you'd like us to, we can.
Yeah, could you please share the slides? I have uploaded them.
Connected.
Yeah, I can
Okay.
do that. Reloading the page.
Okay, thank you. Yeah, so I'm presenting a white paper on detector readout technologies, and the focus is on the future detectors, and we'll talk about the future detectors in kind of retrospective of what we're doing today and what we'll have to do differently. And I'm presenting on behalf of a large group of people who contributed to the white paper. Okay, let's move on to the next slide. Yeah, so the discovery potential of contemporary collider experiments really depends on the bandwidth that we can read out of detector and analyze later on. And so, for example, limited readout bandwidth of experiments like ATLAS requires us to use complicated real-time trigger systems and on-detector buffering of data to pre-select data and to read out the, for example, the data from ATLAS or CMS at reduced data rate. And the trigger system does not have access to the entire event, and it uses some reduced information, and therefore it cannot achieve the same efficiency and acceptance as that's theoretically possible if all the data will be available for processing. In contrast, experiments like LHCb and ALICE can be read out for every bunch crossing, and they don't need the trigger system as complicated as ATLAS, so they can filter data using commodity computing, and they can do it better than ATLAS and CMS basically. That also has, the simplified triggering has advantages that those experiments require fewer custom electronic systems like boards for the triggers and so on. It is simpler to support, it is simpler to upgrade, it is simpler to develop new trigger algorithms, for example, and that speeds up the upgrade cycle. Also, the triggerless readout enables simpler on-detector electronics and more power efficient, since the triggering of data on detector is not required. In some situations, the detector readout bandwidth is limited, not because of cost, but because of combination of technical issues. For example, readout of the trackers in ATLAS and CMS is very challenging because of combination of the power consumption, radiation tolerance of fiber optical components, and bandwidth of electrical cables, and the amount of space we have for the electrical cables that transmit data from the tracker to to opto boxes where data aggregation happens, and also the data goes into the optical fiber. So in a nutshell, basically, radiation tolerant high-speed data links are required to answer the technical challenge of allowing readout of trackers, and ideally that readout should be happening for every bunch crossing if possible. In some cases, like in case of Dune or some other experiments, those experiments can also benefit from data links that can be operated cryogenically at basically liquid argon temperatures to reduce also amount of electrical cables and thermal losses. All right, let's move on. Okay, so let's talk a little bit about FCC HA detectors, and those things need to output about 10 picobits of data per second, and that's a lot. For example, if we assume that our link speed remains at 10 gigabit per second, that's what we have for versatile link plus technology, that needs a million fibers, right? In comparison, Atlas uses about 10,000 fibers, and that's still a lot. So having 100 times more fibers is not very manageable. And so that means that we have to do something about the link speed. On top of that, about 80% of FCC-HH detector bandwidth is from the tracker. And so availability of a rad-hard links can also make an enormous difference on complexity and capability of the detectors. Yeah, if we start looking, from the capabilities of the link itself to capabilities of the detector electronics and modern FPGA transceivers, then what we see that modern FPGAs can do 25 to about 100 gigabit per link, basically per electrical connection. And while we're using 10 gigabit, for example, in the upgrade of Atlas, we really underutilize input-output capabilities of FPGAs. And the system could be smaller or cheaper if we would also use faster data links. And if we cannot increase the speed of data links for the future FCC-HH detectors, that would also mean that we'd need to have enormous number of FPGAs to handle those links. So increasing the speed of the data link also helps to reduce the cost of detector electronics and make it, and reduce its footprint. As you can see, it will be almost impossible to read out FCC-HH detectors without increasing the link speed to, let's say, 100 gigabit per second at least, and without having sufficiently radiation tolerant data links for readout of the trackers. All right, let's move to the next slide. Okay, so let's talk a little bit about what's happening in industry. So in industry, a lot of data links are developed for data center applications. And for those applications, power consumption, cost, and speed are just paramount. And the links for data centers are typically, used for 100-meter range, and all of them are fiber optical. At those distances and speeds, we cannot use any more copper cables because of the very high power consumption. There are basically two technologies for the optical links. One is VCSEL-based, and you can buy transceivers, QSFP transceivers that can run 40 gigabit per second. and one fiber in the transceiver runs at about 50 gigabits per second, which is pretty good. For silicon photonic technologies, it's a newer technology. It's, VCSELs have been mainstream for years, and silicon photonic is emerging, and a few companies are pursuing it. So it offers a similar product. It's a QSFP of 400 gigabit per second. However, one fiber runs there at 100 gigabit per second. And they offer a slightly smaller current consumption than VCSELs, but it's not like hugely different. Maybe it's like 20% smaller. But it's another product that's available on the market. So the industry is playing tricks, the increasing complexity of the system to improve the bandwidths. And one of the tricks they're playing is called wavelength division multiplexing, WDM. And that's used to reduce the number of fibers. Basically, they can pass light at different wavelengths through the same fiber, and they can couple and decouple it on different ends. And this is natively done in silicon photonic links. Another trick they use pulse amplitude modulation for those newer links instead of non-return to zero modulations to encode more bits per clock cycle and to pass data at a higher bit rate. And in Atlas, the majority of links are, for example, I use non-return to zero signal modulation, and we are not using any WDM. But future experiments may require us to get more fancy. Okay, let's move on. Yeah, what industry doesn't do, they don't care about radiation hard links, or they don't care about links that can write in cryogenic environment. And that's something we need to develop ourselves, or select something that's already capable of working in that environment. So far, the majority of data links we've been using in Collide experiments are VCSEL based. For example, Versatile Link and Versatile Link Plus are all VCSEL based. And silicon photonic links are still in development. We also started looking at wireless data transmission or free space data transmission for selected applications, since it allows broadcasting of controlling configuration signal for detectors, and so we can reduce the amount of copper cables that we are presently using for those applications. If we start looking off detector systems, likely we'll still have to continue using FPGAs, since basically instead of some simpler commodity computing, since the on-detect electronics is likely to be synchronous to the beam by using collider, for example, and so we will need to use custom data transmission protocols and for control of detectors. So the FPGAs are likely to stay. However, the connectivity between the FPGA and commodity computing will likely have to go beyond PCI Express Gen 5, and this is what's available now or about to be available, or TCP/IP or something like that. It's interesting that there are CPU FPGA hybrids where they pack FPGA instead of CPU. This can be attractive in principle, since it would, simplify the system. It would have to design fewer custom boards. Unfortunately, those CPU FPGA hybrids that available currently don't allow custom serial links or custom inputs, outputs, and they don't allow user-defined clocks that we need, for example, for the on-detect electronics or for the transceivers. So but I mean, what we're happy with what industry is offering at the moment. So there may be more opportunities for FPGAs or maybe not. But when it comes to optical data lakes, there is nothing we can take for granted. Lastly, if we start looking at effort that goes into the design of detector readout system, and specifically for FPGA firmware, the majority of that effort goes actually in not in the design of firmware itself, but in testing and verification, and that's driven by complexity of the detector and the number of various systems that we have, like calorimeters, trackers, and so on, different protocols. The future detectors are going to be more complex, and the amount of effort that would need to be spent on verification and testing of firmware for readout of those detectors can be just overwhelming. And we can really benefit from novel approaches in design to reduce amount of work we need to do the verification and testing. Maybe there's some kind of HLS high-level synthesis-based approach that can help us make it easier for us to design the readout system. Right, let's move on. Yeah. So let's talk a little bit about rad-hard optical links, and that's basically the foundation of our readout. So we have two major trusts in R&D, and one is happening for VCSEL-based links, another is happening for photonic links. So VCSELs have been and still is the mainstream technology. So VCSEL is abbreviation for vertical cavity surface emitting laser. Right? It's a single laser on an array of lasers, and we turn the power to the laser on and off, and the laser switches on and off. And that's how modulation is happening. Right? And meanwhile, the HEP community cannot develop VCSELs our own. We need to, test and select industrial products that are suitable for radiation environment, for example. And basically, we're limited, but by luck and what industry offers us. However, on the other hand, silicon photonics technology is a little bit newer. We have started looking at it. There's an effort at CERN and other places. But for silicon photonics, we can fully customize the transceiver because it's fabricated very similarly to a normal ASIC. We use wafer and we use regular CMOS process to fabricate it. And so we can design resonators and all kinds of optical components pretty much any way we like, or we can use commercial libraries for that if those are fine, and we can design for radiation tolerance we need to achieve. However, the problem is that we don't have a lot of expertise in our community for this design, and this is something new for us. Yeah, so this may be something we can ramp up in the future if we need to do this by FCCHH. The other interesting difference is that for VCSEL-based links, the data aggregation is typically done logically. Basically, we have a data frame it's built from smaller pieces of data, And this is done by on detector IC like GBTX or PGBT. The silicon photonics, on the other hand, can allow native optical data aggregation using wavelength division multiplexing, where we have few slower data streams transmitted using the same fiber and then deaggregated off detector. Yeah, all right, let's move on.
Sasha, I think we need to wrap up in a few minutes, so we make sure we have time for discussion as well.
Okay, sure, sorry. Okay, I'm almost done. So here is just an example of an older silicon photonic transceiver. You can see there's a PCB and a wafer, the silicon photonics chip, and it has external laser and fiber going directly to the chip. And pretty much all electronics and photonic circuits are built in the same wafer. And the external components is basically a power supply and some decoupling capacitors. And those transceivers were tested for Atlas, for example, and they found to be reasonably wrath tolerant, not enough wrath tolerant for example, for ITK, but that was driven by basically a slow control circuit. But this is a technology that can be really advantageous to the tracker readout, and because of because of the advantages I mentioned earlier. Yeah, so our community can partner with commercial companies to advance this technology and to, so we don't have to develop everything in house, and we can just build the pieces we need and buy the rest from the industry. Okay, let's move on. Here is a specific example of SBR initiative with Freedom Photonics, and the idea is that we can build a silicon photonics IC ASIC that would take fiber in and fiber out, and it would aggregate multiple slower data streams in a single basically fiber. And this is possible thanks to continuous wavelengths lasers that are tunable, and so single laser can output multiple wavelengths, and the data aggregation will be done using WDL on chip instead of using complicated electronic circuit. And yeah, this is an ongoing initiative. Let's talk a little bit about other things. Let's move on. So yeah, so let's switch gears from optical to RF. And we use a Wi-Fi, and for data transmission, it's not as fast as optical, but it works and it doesn't require cables. So for microwave technology, we can achieve data rates of a few gigabits per second, and that uses 60 gigahertz band. And for example, the antenna for that technology is about 1 by 1 centimeter. It's pretty small, and it needs a tiny IC. It's a couple of millimeters in size. The power consumption is low. The bit rate at 1 meter distance is reasonable. And also this is all electronic, so it can be designed to be pretty rad hard. And the other nice advantage of this technology is that the RF signal doesn't penetrate through silicon sensors. And so the crosstalk is a little bit reduced because of that. So this can be used for control, for example, in configuration of the detector to reduce the amount of cables. And let's look at, let's advance to the last slide. This is something more cutting edge, and this is like free space optics. this goes at a few gigabit per second free space over a few meter distance with a pretty good bit rate of 10 to the minus 12. It uses mid-IR wavelengths for communications. Doesn't require any fiber, but I don't know if it requires, if it can be designed rad hard for ATK applications. But as you can see, the portfolio of R&D ranges from very regular fiber optic links to RF and free optics, depending on the application we need to. Yeah, all right, well, sorry. So that's pretty much it.
Great, thank you, Sasha. We do have a little bit of time for questions and discussion still. So start looking around the room here. All right. Anybody remote on the online that has a question? Might not be seeing raised hands, so don't be afraid just to speak up. But Darren.
Thanks, Sasha, for the nice overview of the trends and the technologies and what we need. It's clear particularly for experiments at FCCHH, we need a lot of bandwidth off the detector. Can you speak a little more explicitly about how much, say, the field of high energy physics needs to partner and work on developing these technologies versus are we just following trends in industry? I suppose because of the radiation tolerance, we have to definitely have a leg in there to do testing. But can you make it a little clearly? Put another way, if I were a funding agency rep, do I need to invest anything to support this development, or is it just going to happen? Can you say anything about that?
Yeah, so if funding agencies are serious about FCCHH, they would need to support R&D on rad hard links. So not rad hard will be done by industry. So like FPGAs will be done by industry, right? But rad hard pieces are not going to be done by industry. And so we need to keep an eye on radiation tolerance on VCSELs, radiation tolerance of electronic circuits, radiation tolerance of silicon photonic components. And we can do it through partnership with SBRs. I mean, with small companies via like SBRs, or we can have our own in-house program where we develop small kind of test circuits with just like a ring resonator and MZI, silicon photonics, basically components, and test those for radiation tolerance. And this is what CERN is doing, but it would be nice to have this capability domestically.
Right. Okay, yeah, thanks. There's a question in the room, David.
Yeah, hi, Sasha. This is David Miller. About the VCSELs, this is maybe a naive question, but I mean, it's one of the components that I hear a lot about having, difficult fault tolerance issues as a function of time, and failure rates that maybe we know the mean value well, but there tend to be large fluctuations. Is that that's not, as far as I understand, always been related to radiation tolerance specifically, right? I think we've seen VCSEL failures in very low radiation regions. Is this something that is coupled to the is the robustness and low failure rate that we would want and hope for such a large number of VCSELs something that is likely to be improved with the radiation tolerance studies and improvements, or is that a sort of separate line of R&D at some level, or am I just off base?
So David, yeah, thanks for the question. We cannot easily improve radiation tolerance of VCSELs on our own. They're developed by companies, and we just test VCSELs from different companies to pick the product that has highest write tolerance. That's pretty much all we have been doing. And it's for Atlas, for example, CMS, it's not enough to read out tracker directly. So we rely on electrical cables to put voxels where they can survive. And I'm not sure this is going to get any better in the future, since voxels are very sensitive to defects, and the radiation produces defects in the semiconductor lattice. So it's going to be even more challenging problem for FCCHH.
Okay, thanks, Sasha. Maybe a follow-up on that, just to, I mean, so even beyond, I mean, are silicon photonic links more fault tolerant even beyond the radiation issues?
So for silicon photonics, basically the laser can be external, and the modulator, they rely on the refraction index, for example. So those they can be designed basically a little bit larger to absorb some defects in the semiconductor lattice. And we can, CERN is doing it already. So they've shown that they can customize the design of the modulator to be rad tolerant as they need it. Of course, there are some, how can I say, thresholds they cannot cross. If the radiation is too hard, then everything is destroyed, everything is melted. So, there is a limitation, but so far they have very promising results. And if you're interested, there are links in the white paper to what CERN has been doing. But they recognize the importance of this technology, and they have started R&D quite a while ago.
Great, thank you. And any other questions? Not seeing anything around the room or online. So thank you again very much, Sasha.
Thank you.
Thank you. Thank you to everybody who contributed and worked on this white paper as well. Okay, so move on to our next talk on TDAC innovation.
Following your lead, should I run up?
What does that mean? Do you want me to control the slide?
I'm not sure.
You have nothing to control the slides there.
Okay, yeah, I don't feel like I get all Johnny Mnemonic on people here. Nobody remembers that movie? It's like my favorite Keanu Reeves movie.
You do have a pointer here. So
Okay,
use that.
great. Right, yeah, Zoom.
It's okay.
Okay, that's okay. We have a small local audience. Okay, well, that comes up. Let me just preface this by saying, maybe this is obvious, but this is effectively a summary of a contributed white paper. And one of the things that we early on discussed with the topical group conveners was that at some level this would be kind of a not quite a catch-all. That's a little bit too denigrating a description, but something that would allow for communicating some of the innovative ideas that were contributed, as well as other things ongoing in the community, for example, from LHCb that we've heard a lot about in other contexts, and make sure that that gets communicated up the SNOMAS, P5, PPAP, et cetera, chain. Okay, so this is not meant to be completely all-encompassing. There are dedicated white papers on other topics, but we've tried to cross-reference when and where possible. Okay, and so with that said, if you could go to slide number 2, just to set the stage a little bit, and I'll probably gloss over some of this since we have a room full of experts. Basically the idea is that there's a lot of challenges to be faced. Sasha just talked about some, we'll hear about more later, and we have a pointer to some of those in the slides for people who end up looking at this sort of thing offline. And basically the idea being that there are a host of challenges, and we've tried to distill those down into a couple of categories. in particular, also pointing out something that we've actually heard quite a bit just in the past few days, and that's that this technology does not develop and implement and commission and operate itself. Okay, so that's going to be a key takeaway. Pardon? Oh, and so on slide number 3, actually we've tried to put this kind of a bottom line up front. So if you decide to tune out over the next 14 minutes, these 3 takeaways are effectively what we'd hope you bring with you. So let me just give you the short version, sort of use old stuff in new ways, pursuant to the point that was made a minute ago, that there are technologies developed elsewhere that we need to often, and we do, figure out how to implement to achieve the goals that we envision, despite the fact that they were developed by some industry, with some industry goal in mind. Get new stuff to do what we want. In particular, that means kind of, again, pursuant to the comment I think Darren was hinting at, which is feedback to industry and help drive some of that development, and that is something that as a community we should take seriously and address conscientiously and explicitly. And the last is perhaps one of the most important and most difficult to implement programmatically, and that's to build and train a sort of knowledge-based community. Like I said, this stuff doesn't figure itself out, and we as a community develop enormous expertise, and for a variety of reasons that's easy to lose. And making a very concerted, field-wide commitment to trying to preserve that knowledge, and more importantly, those people, is extremely important. Okay, on slide number 4, please. So to summarize, we put the various ideas that we decided to incorporate into this white paper into sort of 3 categories. The first is novel applications and uses of sort of commodity and custom hardware not customized for us, but which we are deploying for our own use, including firmware and software. And that's very important. And actually, there are people in the room who are pioneers in this sort of regard. Confronting state-of-the-art devices with the needs of our community, low latency, high throughput, high performance. Perhaps we should include in high performance radiation tolerance, for example, following on Sasha's talk, is also extremely important. And oftentimes, as hinted just a moment ago, these requirements and specifications go beyond what is typical in industry contexts. And so making sure, to the extent possible, that we close that loop is extremely important. And just to reiterate, the acquisition and retention of people, including their knowledge and expertise, is extremely important, especially when integrating, commissioning, and operating these enormous, and what we are going to, communicate, heterogeneous and complex systems. It takes a long period of time, and it doesn't just end when you connect the last cable. Okay, slide 5, please. Okay, so I think that this is pretty much common knowledge for most of the people that I see in front of me, and the few names I had seen on Zoom. So again, apologies if I go over this quickly, but I think it's appropriate. We have a lot of challenges and operating conditions that we need to face, and some things that we will actually hear quite a lot about in the rest of this session this morning benefit from dedicated challenges. That is, the actual technology is inspired by specific challenges. For example, long-lived particle searches and fast track reconstruction, and confronting that with modern technology. So this, to state the obvious, perhaps for many of you, has involved lately a massive kind of reimagining of exactly what sort of devices are included and involved. And basically, the summary is that we've developed as a community very heterogeneous large-scale systems where we're incorporating and using with one another CPUs, GPUs, FPGAs, ASICs, systems on chip, and so on. Sometimes all on the same board. Okay, most modern system on chips have CPUs, GPUs, and FPGAs all in one package, for example. Okay. And so, as mentioned, there are several talks just in this session We can finish up the hyperlinks there. I don't think they were all uploaded when we finish these slides, so thank you. Okay, on slide number 6. All right, so a couple of the challenges that we decided to focus on, again, given also the scope and structure of the white paper, are, for example, signal extraction in the low energy regime. So you can think of, as an example, the Dune FAR detector, where for certain physics goals, you may want to, for example, lower thresholds significantly in order to extract certain physics parameters. And that becomes obviously very challenging and an enormous detector condition like the Dune FAR detector. High data rates, but which, for example, may also include analog readouts. And therefore, again, you're talking about a complex system of, in this case, for example, RF, ADC, and eventually, digital signal propagation, but which requires a sort of scalable architecture and nonetheless very high rates, for example, in Project 8. And then lastly, computational approaches that follow on from all of these devices, and that use the signals from all of these devices simultaneously, even across multiple facilities. So this may not be as common in this common a discussion in this community, but this is something faced, for example, by multi-messenger astrophysics when they're trying to combine literally several different, global facilities in order to provide alerts, for example, for gravitational wave detection. You're dealing with an enormous number of data channels to begin with, and then on top of it, trying to sort through different sorts of detector signals and their sources, and still providing low latency estimates. This creates a wide variety of challenges. So on slide number 7. One of the things that we tried to highlight is that there has already been a lot of work in this regard. And one of the things, for example, that you've seen from LHCb is the fully GPU-based implementation of their trigger design. And there have been a variety of proposals, some of which are already being developed with prototypes for mu to E, for heterogeneous device integration for their readout system. And of course, one of the things we already heard about yesterday from Jan, and many of us have played around with as well, are a variety of machine learning or machine learning-like, basically, novel, more sophisticated multivariate algorithms in the trigger system using the enormous number of resources now allowed for by modern devices. And so all of this, including a few wacky ideas related to also some of the things discussed yesterday, are based on the availability of the sorts of devices and technologies that we have in hand now, but are still really at the stage of being incorporated into our community and developing the expertise to actually deploy them at scale. And so once again, that's going to be one of the concluding remarks from this talk. So on slide number 8. Moving beyond some of the sort of very device-specific concepts, we are really talking about, coming back to Sasha's talk once again, for FCC-HH, we're talking about millions upon millions of readout links, potentially, all connected to sources of data on detectors that are providing extremely high rate and high bandwidth outputs. And so the sort of hyperdimensional DAC and processing system is one in which you're really dealing with this bandwidth issue head on, almost literally, but also, we're going to hear about this from a variety of other frontiers, in particular the computational frontier, regarding the necessity to not only preserve our data, but also reproduce results as we go forward as a community. And depending on how you think about the timeframes discussed in yesterday's accelerator task force projections, we are talking about, decades where we may be considering, looking at and re-looking at data. And so this is extremely important. But to some extent, how you collect that data will affect the ability to do those jobs. And so again, that's where we have brought to bear some of the discussions and contributed ideas for innovation. So on the next couple of slides, We'll focus on asynchronous, hardware triggers, certain edge computing ideas, and streaming DAC with a little bit of a focus on the first and third. So on slide number 9, please. And how am I doing on time? 6 or 7 minutes?
About 10 minutes.
10 minutes. Okay. All right. So for the first example, this asynchronous first level trigger idea, this may or may not be something that people are aware of, but at some level it has already started to be incorporated into some designs. And the question is, can we explore this more broadly as a concept for basically trigger and DAC systems overall and looking towards the future? So the very brief summary of this concept is to turn the trigger and DAC system into a sort of event-driven as opposed to clock-driven approach. And this is not something that has never been done before. There are examples of this, but again, in many cases, it was not part of the initial design of the overarching system for the trigger and data acquisition of the experiments in which you see this. There's a bunch of text here, but basically the idea is to sort of blur the line between the sort of very fixed latency clock-driven concept that we have in many of the first level triggers in experimental particle physics, and the, like I said, event-driven approach in the higher levels. And so one of the things that is necessary for this is dealing with the time multiplexing and demultiplexing of the signals, the arrangement of the optical links that are involved. I mean, this again harkens back to a few of the things that Sasha was referring to, and their usage in a system, and thinking about then also how to incorporate FPGAs, CPUs, and GPUs to execute a mix of very fast, precise algorithms with this time multiplexing and demultiplexing of the front-end detector signals. So if you go to slide number 10. Building on this, although focusing more on the data acquisition aspect of it, a concept of streaming DAC provides the ability to, or conceives of the concept of basically reading out the detector at the full data rate, but effectively tagging the data that you receive with a time and likely location stamp, and basically allowing for a triggered detector readout that allows for the DAC path to provide full readout for the front-end detector electronics. And so the idea here is, or rather, the historical progression of this idea is that this is not possible because of a lot of the limitations on the output end, on the data acquisition side of things. Either, I can actually try to use this, either you can't process the data at the full rate, and some of those ideas are now being challenged, or you end up creating unsustainably large data sets, which again, our computing system colleagues are addressing head on as well. And so the concept of this streaming DAC is to essentially work around these rate and bandwidth limitations to try to get the most out of our detector signals. Again, the idea being that we've built these amazing front-end sensors, let's try to get as much of the data as possible. So if you go to slide number 11, basically, I'm going to summarize, I'll skip over for a second the limitations that have built up over decades in terms of the current paradigm, and point out that basically, this idea of trying to read out the full detector into the DAC system is in part reliant on the idea of applying thresholds and suppressing some of the sparse detector readout that we know exist at the front end. And therefore, to get over some of the downsides, such as loss of information, selection biases, et cetera, not to get rid of them, but to work around them by approaching this in a little bit more of a sort of parallelized, continuous, again, streaming mode with the time and location of the data tagged for processing within the DAC system. So if you go to slide number 12, basically the advantage of this is that is based on aggregation. And trying to basically get many streams together, again, multiplexing and demultiplexing the data, and doing it in sort of a time-based approach. And some of this actually in both Atlas and CMS is already being explored. But again, the systems were not necessarily designed from the ground up to do it. And so I'd say that one of the key points here is that the event building, the putting together of the data, is now done after the data have reached an eventual sort of output location from the data acquisition system. And the upshot of being able to do that is that the event processing, or high-level triggering, if you will, can now be done effectively asynchronously. And so the front-end electronics, and in particular the depth of the buffers there, are no longer the exact limitation. So one of the things that's key for this is the high-performance computing, which we now effectively rely on as part of the paradigm of our future systems to begin with. What it does is hopefully reduces the complexity, again, hearkening back a little bit to some of the things Sasha said about the custom hardware trigger, and the interweaving with the tiered storage and parallel processing system of the downstream compute architecture. Okay, slide number 13, please. So the last thing that I want to touch on after covering those few examples is the fact that these systems are, as we probably all know, enormous and complex. And again, their construction doesn't necessarily end with the connection of the last cable, okay? Because it still has to be implemented, installed, deployed, commissioned, and so on. And the transition from that sort of final testing stage to the execution and operation stage is often longer than the construction itself. And it really is extremely important to invest adequate effort and pay equal attention to those steps, okay? And without these efforts, data taking, is ultimately compromised, and as we all probably have examples of, and it becomes difficult to actually meet the goals because we have this wonderful system, but the actual deployment, commissioning, and operation of it is still just as complex sometimes as its construction. Okay, there are a few points here, but let me move on because I want to make sure we hit the last bullets. We decided to include this somewhat tongue-in-cheek but very important statement in the white paper itself. Actually, we'll see how many of you actually read it and caught it. But the idea is, that oftentimes this aspect of the experimental effort is either undervalued, underappreciated, or all of the above. And that it's incredibly important to recognize these people, because at the end of the day, we are all people doing this work. And the fact that, it's oftentimes the knowledge base that's instilled and carried by those people that makes the deployment of these extremely complex systems possible. And so this actually dovetails with some of the discussion in the community engagement forum, in fact, that, sort of career progression, long-term retention, et cetera, is all critical to actually making these facilities themselves successful, that it's not just the stuff, it's also the humans, strangely enough. So on slide number 15, one of the things, that you will have seen lately, including in Joanne Hewitt's talk on Sunday, is that the structural elements and programs and facilities to attract and retain these people. You can see from a very high level at HEPAP from Glenn Crawford, an extremely important charge right on slide 7 about this task is already very apparent. So on slide number 16, one of the things that we wanted to say in terms of our final remarks is that, on that particular point, is that these innovations can only be brought to life if we acquire new domain knowledge and if the people are kept around to see it through. Coming back to the beginning of these points, though, I think the summary is that we sort of appear to be at a little bit of a threshold in which we are thinking about, and hopefully, I hope, designing new facilities. And incorporating these ideas in their conception is extremely important because it can play a huge role in how every element of the detector design is then executed. And they're really going to be essential for the success of future facilities. Sasha has already made that point very well. And current experiments have really done an amazing job at pushing scales to the practical limits, but we're really going to have to go, orders of magnitude larger along some axes in the very near future. So if you go to slide number 17, we tried our hand at maybe providing a couple of bullet points that might help to deliver this message up the chain. So let me just read these out loud because people may have important comments. The field should explore and invest in paradigm shifting approaches that can bring TDAC systems to new levels by leveraging new technologies and creating partnerships, again, back to Sasha's point, to meet the goals and challenges of these next generation facilities, and that the facilities and programs themselves should be structured and funded to identify, acquire, and retain the people and the knowledge to make the leap to a new generation of technology. Thanks.
Yeah. Questions, comments?
And I'll repeat the question for people on Zoom. Go ahead.
It's about the integration and operation.
Yeah. So maybe if you could go back up to slide 14, I think it was. Or 113, maybe. Anyway, go ahead.
Yeah, I think other detector technologies do a good job of creating a critical mass for like test beds and things like that. And I think we don't do that.
Yeah. So Nyan,
I'm wondering if there's like a thought on how we could sort of.
yeah, great point. So just in case Nyan Chan pointed out that there in terms of front end detector technology, there's often an enormous amount of effort put into test beds, prototypes, test beams, and so on, where a lot of bugs and kinks are at some level worked out, not all of them.
Over and over again.
Yeah. Yes. But that may not always be the case for these sorts of, in many circumstances, distributed systems, heterogeneous electronics, et cetera, which are not part of the front end signal collection. So yeah, absolutely. And actually, I had the opportunity to talk to some people from shoot, I'm blanking on the name now. There was this, it's basically one of the continuous integration back-end systems. And they were doing it at Intel with banks of FPGAs, right? Rooms full of FPGAs where you would deploy firmware on 50 FPGAs at the same time and run everything, as you're saying, with basically a demo room. And stress test the systems, and we don't have systems like that often. But it's again one of those things that I think we could learn a lot from industry about, because they're clearly doing it. But we would have our own goals with those sort of test bed systems, if you will, or demonstrator systems. And moreover, one of the things that we've been able to do in Atlas, but just kind of piecemeal, is to then use that as a deployment platform before putting things into production, so to speak.
We also extend this to R&D platforms.
Yeah.
This happens a lot also on the computing side, like full processors.
Mhm. Yeah, Nyan's point is, on the computing side, they have examples of this, and we should think about adopting it and at the sort of intermediate stage that we're at with this sort of system. I completely agree.
Did you mention the detector level simulation tool that allows you to simulate what you'd like to have, then use these sort of continuous integration techniques to put in the pieces that you're making, and then see how that affects the larger system? We know enough now, I think, that we can talk about detector level simulation. I wasn't sure that you brought that up.
I did not bring that up. No, that's a very good point. I think that the ability to make estimates for what sort of impacts the readout system, the data acquisition system will have on the utilization of the front end detector signals is not something that is often done.
Each of these subsystems that you're modeling so that you can get the data off the detector has their sort of own rate to keep up. And if
Yeah.
you lose the ability to trigger on an event by event basis, and you want to say, well, what will be lagging behind? Where do we have to focus our efforts? And that probably comes most truthfully out of the simulation.
Yes, but I would actually go beyond just the simulation, and something that we didn't cover in this talk, but there was a contributed letter of interest and paper, and it actually came up in the discussion yesterday, in part from David Shee on the machine learning side, was that we can try to use information about the data that we discard as well, meaning that if we implement a system where we can basically keep track of in real time of the data that we have thrown away, we can also use that to assess something about the data that we have saved and feed that back to the simulation, which we generally train only with the data that we have collected and retained. So I think that there's
physics output part of this in that simulation and so that's true.
Yes.
And that you might be able to say that are valuable or not valuable.
Yes.
Your point would be very important when we start to get more complex, like event-driven data, like we're not meeting everything else. It's not so simple now. It's coming, and that's, I think you're right. Yeah, that's simply.
I mean, so we've had these kinds of issues on like for our NTP, where it's a more event-driven readout. And as we're integrating the detector, and then we start to inevitably push to higher rates than we necessarily were imagining, we start to see these kinds of complex sort of behavior evolve, which is, the interactions of various computers with the networking and file up of various things, and where you start to see them slow down and all of that. Having some work done ahead of time, facility to do that in simulations ahead of that would help us with a lot of that. Also better understand what those issues are rather than just kind of fix things on the fly and then you got it to work and so you're happy. You don't really understand what's going on.
This would be a lesson from what we learned from Michelle LAC. So I'm sure.
Sasha, I think I saw your hand raised at one point. Do you have a question?
Yeah, I have a question to slide 9. At the top, there is discussion about, high precision timing and low jitter clocks. And like, I'm confused. Why is it related to a synchronous trigger?
Well, because if the DAC system is clock driven, right, then you are intimately, then the fidelity of that readout is intimately tied to the precision of the clock. And so if you are attempting to do any sort of time of flight measurement that requires we put order 10 picoseconds there, right? Because there's this goal of 50 picosecond precision for measuring various for differentiating between different particle species, then you are then the precision of the clock itself is extremely important. This is not obviated, but is different.
I think I understand what you mean, David. Yeah.
Let me just finish my sentence for I don't know, completeness. It's obvious, but different in the case of an event-driven asynchronous readout or pipeline, because then you're only required to be precise in that timestamp, not the full operation of the clock. So
you need a timestamp for the labeling the data.
Yeah.
And after that, it's just.
Exactly. Exactly.
But in both cases, you need to intercalculate that the 10 people second.
Don't worry.
Yeah.
Just to clarify something. In Atlas, a lot of readout is already asynchronous for phase 2. Like ITK is pretty much asynchronous.
Yes,
and readout of a lot of all this fast timing things is asynchronous.
yes.
So the data is timestamp. It doesn't really depend on the sampling clock.
Right,
Yeah.
and that's the examples you just gave are for data sources that are not included in the first level trigger. Right, and so the idea here is to have that be a system. The concept is that this is now a system-wide architecture choice. And the second to last major bullet point there says, in fact, already not even HLLHC, there are some portions of the LHC first level triggers that are like this. And the idea here being that you build a system with this as the core concept.
Yeah. I mean, it's impossible to rely on precise picosecond synchronization, in a large system. So yeah. Okay, thank you.
Yep.
Okay, so there was one, but maybe I can bring it up. No, I can't. Question from Chelsea: do you have plans to develop using diesel ACAPs? Maybe Vexel ACAP?
Versal. Versal ACAPs. So let me just, remind, I mean, part of the point of this talk was to summarize the white paper. The white paper was, part of the contribution from many different people doing many different things. I am aware of people absolutely looking into the use of Versal in many different applications, not only Atlas and CMS, but also outside of that. So the simple answer to your question is yes. Now, I think the maybe part of the deeper question is, given that these Versal ACAPs have components on them that are specially designed, for example, these AI engines, or even maybe more simply, just a much larger number of high bandwidth transceivers. The answer is that yes, my response is that the incorporation of that sort of even more heterogeneous single device in and of itself is already being explored, and what that would look like in a LHC detector experiment trigger system. To what end could the AI engines in those Versal ACAPs be used? What is their specific utility? What are the drawbacks? What are the costs? Etc. So I'm aware of plans, for example, in Atlas to use some of the premium series with but without the AI engines, but just because of the larger number of high bandwidth transceivers. So I think the answer to your question depends on some of the details, but the simple answer is yes.
We are past our allotted time for discussion. Thank you very much.
Thank you.
Thanks everybody for the discussion.
If you have a comment, you're also welcome to insert it on our Google Docs.
Yes, absolutely.
We can combine. No other way.
And if you do have things that you haven't gotten to yet, then we will have more discussion time after all the talk.
Yeah, that's right. Okay, so we will move on to Christian to give us an overview on tracking triggers.
Hi there, can you hear me?
Yes, we can.
Okay, very good. Shall I share the slides or will you do it?
If you can, that would be a little bit easier, but if you'd like me to, I can.
I think I can. Give me 1 second. Okay, I think you can see that. Yeah, okay. Oh, but there's a... Okay. All right. So apologies, I can't be there with you today. I had a prior commitment within the experiment, so I'm in Europe at the moment. But hopefully this connection is okay. So I will try to give some quick perspectives and outlook on hardware tracking. On slide 2, so I think everybody knows that tracking is essentially one of the most computationally intensive aspects of reconstruction at collider experiments. And because it will factor into sort of what I'll discuss in a minute, I just wanted to point out that this typically involves at least 2 conceptual processes. Sometimes they're merged, but processes that involve track finding, which is a pattern recognition step that performs the association of detector hits with a single trajectory. And then track fitting itself, which is of course used to obtain the kinematic variables from a trajectory fit. Typically, tracking algorithms are iterative and they dominate the overall construction time for experiments. And this gets worse basically as pileup grows. So as you have these soft overlapping collisions, the complexity and the processing time for pattern recognition in particular is going to scale as a power of the number of vertices in your detector. And pileup itself is going to grow as the instantaneous luminosity of the accelerator increases. So on slide 3, the situation is even more challenging for online track reconstruction. So tracks are needed by trigger selection algorithms, either in hardware or in the HLT. And the online environment is going to impose additional constraints on the processes. So just to give an example from run 2, the level 1 trigger hardware and CMS had an overall 4 microsecond latency budget in run 2. And the HLT, the software-based HLT, had something like 260 milliseconds. So it's not a lot of time to actually track all of the particles when you have substantial pileup. In addition, online algorithms generally operate with reduced inputs or precision. This is either because of that overall latency concern. So you have some amount of time to process, and then after that, you have to stop. And that will lead to inefficiencies that are sort of reflected at this plot at the bottom right. Or simply just because you can't read out certain detectors within the time you have available. So for instance, pixels are typically not read out for any sort of level 1 trigger just because of the sheer volume of data and the short amount of time to do it in. So on slide 4, so what I'll talk about is trying to improve the performance of online tracking in particular using hardware. And I'll touch on sort of 3 ways in which folks have looked at this. One is in hardware level 1 trigger systems themselves, but then also as hardware custom coprocessors for a software trigger. So trying to use the hardware to accelerate the HLT. And more recently on heterogeneous commodity accelerators, also in the software trigger systems. So what I thought to do is basically try to review the recent history from Atlas, CMS, and LHCb in terms of tracking and triggering, mainly because there's been a lot of development and a lot of disruption sort of reflected in the evolution of the plans of these experiments. And from what has gone on in the past several years, I'll try to draw some conclusions in terms of what that means for future experiments and upgrades. So slide 5. So in run 1, Atlas, CMS, and LHCb all kind of started with similar, let's say, conventional triggers. So they all had a hardware level 1 trigger that was based on calorimeters and muons. And then the tracking only came in at the HLT level. And typically, this is where the pixel information is also pulled in. So this is kind of a generalization. There are, of course, some differences when you look into the details. So for instance, Atlas has the concept of regions of interest, and the tracking was performed within the ROIs in the level 2, which was a CPU farm. LHCb, if you look at the table of rates here, has a much larger rate out of the level 1 trigger than Atlas and CMS, but they also have a smaller event size. But by and large, kind of the split between hardware trigger and software trigger existed sort of across the board back then. All right, so on slide 6, this is just my illustration of what happened sort of after run 1. So we had this nice tight grouping of sort of designs of the online systems that kind of went their separate ways, starting in run 2. So to quickly review on slide 7. So first, just one slide on LHCb. I think as folks know, starting in run 3, LHCb is no longer utilizing a hardware trigger. So this was removed, and that means that there's a 30 megahertz rate directly into the HLT. And in this plan, they're performing full tracking on GPUs that are co-located with their first step of event building. So the GPUs are in this box along with the networking that's required to bring in that 30 megahertz rate. At that sort of first stage of their HLT with the GPU, they're performing very simple track selections and then a full sort of offline quality reconstruction at a later stage of their HLT. And one other thing to note is that they're performing object filtering for about 2/3 of their output data stream, which allows them to significantly reduce the output rate to tape, with the caveat that reconstruction of those events is no longer possible. And so I thought to just highlight here from a paper from LHCb that they have the first complete high throughput GPU trigger for HEP. So on slide 8, so now moving to Atlas. So in phase 1, Atlas had a plan for a custom hardware system that could be used to bring tracks into the HLT. This was designed to operate with the full tracker coverage, 8 layers from the semiconductor tracker and 4 pixel layers. And this was going to perform global tracking on every level 1 accept at a rate of about 100 kilohertz. And this was to provide tracks all the way down to 1 GeV to the HLT with a latency of 100 microseconds. The pattern recognition, as I mentioned, it's the main challenge, I think, in the hardware tracking systems, and especially as pileup grows. And so Atlas intended to tackle this using an associative memory. And so what this is a custom ASIC that, at least in the first iteration, is at 65 nanometers. And what this ASIC does is sort of in real time allows to perform that pattern matching of the semiconductor tracker hits with a bunch of stored patterns that are in the chip. And so integrated over the system, there were 1 billion patterns. And the idea is that basically as you latch the input hit data into the chip, as soon as all of that data is latched, you can have pattern matches sort of coming out in very few clock cycles afterwards. And then based on those patterns, you can then perform that linearized track fit with the full resolution hits from all of the layers together. On slide 9, so there was a sizable backend system foreseen for the FTK. So it was something like 2,000 FPGAs total, those 8,000 ASICs that I mentioned, the AM chips. But the project was actually successfully slice tested in 2018, but the project was canceled in 2019, and I've included some text here from some of the reviews highlighting what I think is kind of the most relevant. And here, one of the grounds that was given was the significant gains that you get just from optimizing the software tracking system itself. The FTK idea, so this phase 1 hardware tracking system for Atlas later evolved into an idea for a hardware tracking for the trigger, so HTT. This looked at using a next generation of the AM chips, now down to 28 nanometers, storing about 4 times the number of patterns that were in the previous AM06. And sought a streamlined system design. So you would have one sort of flavor of main board, which helped with some of the complications that were encountered with integration. The performance of the system would be a bit higher, so one could perform regional tracking at a 1 megahertz rate and global tracking at 100 kilohertz. And the idea here was to use the system as a coprocessor for the event filter. There was an option that was explored for looking actually at a level 1, what I call a level 1, but I think level 2, but I think in the Atlas nomenclature was level 1 regional trigger. So this is directly in the trigger path that would perform tracking at 30 microsecond latency at about a 2 to 4 megahertz input rate. This sort of evolution was canceled in 2021, and again I tried to list some text from reviews and highlighting what I think is relevant. The first one was in the context of the level 1 path, so the hardware trigger path, where it pointed to risks in development to the front end ASIC as being a concern. And then for the coprocessor for the event filter, there was mention of the need to sort of explore commercial solutions. Now switching to CMS, quickly, I won't discuss the development for GPUs. What I'll focus on is the hardware tracking for the level 1 trigger in CMS. This is a phase 2 upgrade, so targeting the high-lumi LHC. And this is enabled by the use of double-sided modules in the phase 2 outer tracker. So this is kind of a sandwich of 2 modules, and then the ASICs that read them out are able to identify correlated hits, which are called stubs in the CMS language, that give you a trajectory that is a short trajectory that's consistent with down to 2 GeV for tracks. So that stub data is then multiplexed with the full resolution sensor hits on both layers on the same data stream going out. And actually, it's kind of ironic if you look at this, about 80% of the CMS outer tracker's data stream now consists of trigger info. So information that's destined for the level 1 trigger and not for DAC readout. The stubs are sent over there's a 2-layer system. The stubs are transmitted from the readout to a trigger board over 25 gigabit per second links. The aggregate stub bandwidth for the system is about 50 terabit per second. This is performing full tracking in just the outer detector, so no pixels, in about 5 microsecond, including I/O. Those fit tracks are sent to the global level 1 trigger and used in particle flow algorithms, and then later forwarded to the HLT. Slide 11. So the gains from level 1 tracking in CMS have been pretty well established. So there are a number of benefits from doing this in terms of resolution and efficiencies. There's also, of course, potential for tracking long-lived particles already in the trigger. In terms of the implementation in CMS, so there were 3 proposals for this sort of hardware tracking system. They were all demonstrated. One of them was associative memory based, so following on from what was done in Atlas. And then 2 that were fully FPGA. The AM options included the chips that Atlas was considering, but then also a 3D stacked version with through silicon vias as well. But in 2017, there was a decision within CMS not to pursue the associative memory option, basically pointing to the risks that were involved in going down to the smaller feature size and potentially the 3D. So what has moved forward in CMS is a hybrid of the 2 FPGA algorithms, where there's a sort of traditional tracklet road search to do the pattern recognition, combined with a Kalman filter fit. This will be run on approximately 200 boards, each one of those with dual VU, so Vertex UltraScale 9P or 13P FPGAs. Okay, so that was a very quick summary of the recent history. So now I will try to give you some of my thoughts as to what this entails potentially for the future. So on slide 13. So the first thing I sort of take away from this is that modern FPGAs have become incredibly powerful. If you look at the logic that are on these UltraScale Plus high-end FPGAs, it's really kind of phenomenal. Sort of coupled with that is that all of these FPGAs have a lot of high-speed transceivers as well. And so this now is also very commonplace, and people are utilizing these throughout the online systems. So what I take away from this is that really significant processing power can be brought to bear on a lot of data very quickly, sort of combining those 2 developments within the field of FPGAs. What that means is that we've kind of diminished then the need for custom ASICs in the backend systems for trigger and DAQ. And this is really, I think, a stark difference with respect to not really that long ago. So I show a picture here of some of the level 1 electronics from CMS from run 1, and you can see there are a lot of ASICs that are custom ASICs that were on those boards. Whereas today, there are no backend ASICs that are really foreseen for phase 2 for the high-lumi LHC, either for Atlas or CMS. So there really has been sort of a phase change here. On slide 14, so a little bit more on ASICs in particular. So I'll note that the particle physics is kind of remaining on the lagging technology nodes. So I think the lowest we go is 65 nanometer for high-lumi LHC. part of the reason, or one of maybe the main reason, is that the designs start to become much more complex and costly at the higher nodes. And in particular, the amount of time that needs to be spent on design verification grows significantly. And that's quite an expensive aspect of the process. Many of the design teams for ASICs are already under strain. This is reflected, for me at least, by the establishment of the CERN chip service that is meant to sort of help the experiments try to fill this void, and by sort of the rise of these collaborative design efforts, like RD53, for example, where one institution now can no longer really afford to sort of do things on their own, and it makes sense to sort of pool efforts. We're, of course, also a very small player in a very rough market. And I think what we've seen in the evolution of these systems, both in Atlas and CMS, is that there are assigned considerable schedule and budget risks that are associated with ASICs. And that's gotten, of course, even worse since some of those decisions had been taken. Of course, we can't completely avoid that in HEP, in particular for the front ends, but I think there is a strong desire to minimize those risks where possible. On slide 15, so for FPGAs, FPGAs themselves are not without risk. In particular, I think it's unclear if level 1 tracking would be supported as well as it is now as FPGAs shift into sort of co-processors, right? So there's a clear movement, I think, of FPGAs towards the server in terms of heterogeneous computing for AI, for machine learning, for analytics. And the question here is, will the market end up constraining our flexibility to design custom systems? Is that even something we're going to want to do necessarily in the future, depending on how the hardware evolves? Will we essentially be forced to work completely within AI paradigms, if that's where the market goes? And if that's the case, how well would our sort of single-minded algorithm, something like the tracklet, for instance, how well would that perform on hardware that is really optimized for something else? And then lastly, as we start to move in and really people are carving out market here, one worries a little bit that the devices are becoming less generic. And so perhaps we get locked in a bit more in terms of vendors and platforms and toolkits. And here I'm quoting some text from Xilinx for one of their accelerator cards, where it's pointing out that there are special FPGAs that only run on that card, and it's not something you can buy necessarily off the shelf. Quickly back to ASICs on slide 16. So one of the other things that I took away sort of from the history is that the integration of trigger capabilities in the front end is kind of crucial for level 1 tracking. In CMS in particular, this is what allowed the stub sort of formation is what allowed an immediate sort of rate reduction of a factor of 10. Which then allowed the rest of the design of the system to work. And this sort of tight integration of both the triggering and the readout sort of facilitates detector optimization that could be done simultaneously, both for trigger and for DAQ. In terms of the integration of future real-time tracking functionalities, so far the ASICs have really only dealt with the outer trackers in particular. The obvious step is to try to extend this, I think, to pixels. Timing information is not being used at present, so if one wants to perform something like 4D tracking, one needs to include precision time information. This is anyway going to be required at experiments, say at the FCC, to cope with the very extreme pileup scenarios. One thing that is kind of a neat idea, but it's probably quite difficult to think about how one would do it, is extending the sort of stub picture into intermodule correlation, so something like hardware tracklets or triplets. If you start communicating across modules, how can you do that very quickly? Maybe there's some folks thinking you could do this with wireless, as 6G is converging on something like a 10 microsecond latency. That might make it possible. But in all of these cases, one really has to also then look at the power and the mass that would needed to be that would be needed to achieve those sort of goals. One more thing on slide 17 on FPGAs. So I wanted to mention that the toolkits here are really helping to promote the engagement of physicists in the design of hardware systems. So for instance, the CMS hybrid algorithm is using HLS, so high-level synthesis from Xilinx, which allows students even to write C++ and then have that be converted into RTL that can run on the FPGAs. And of course, HLS for ML is used throughout the CMS level 1 trigger system. Atlas, I think, is looking at sort of analogs to HLS, so SYCL and one API that allows you to write a code base that can run on any number of heterogeneous accelerators. And this is really good because it helps us to broaden our involvement beyond really the hardware experts. Finally, I think this came up sort of at the end of the previous talk, is system on chips. So this is FPGA logic plus CPUs like the Zinc, the Versal, etc. There are planned use for this in the High-Lumi LHC, kind of at this moment, at least on the blade control and interfacing side. But they're pretty attractive because they're affordable, multi-core, including real-time cores, they're low power, and they have these new, at least some of the devices now have these on-die AI engines. And so the obvious question is, could you try to benefit from those aspects in an online tracking environment? Here, I think the real concern is still the latency. So that's something that one would have to look at. But I give an example here of where it is being used in GFACs. Okay, finally, in terms of future experiments, now explicitly, so the example that I'll take here is the FCC HH, because the specifications are pretty intimidating. So this would be a 30 gigahertz PP collisions, giving you a 4 terahertz track rate at 1,000 pileup, and the pileup is going to be a factor of 10 closer than it is in the LHC. If you look at this, and once you get over your initial shock, you realize that this essentially poses the same design choices that we're already facing for the LHC, but now maybe kind of on steroids. So the options just kind of generically is, do you look at a hardware level 1 system with an HLT, where you're performing a lot of intelligence selections already at the level 1 to cut your rate down to the HLT, and that's going to require the high performance on detector processing. If you have a multi-level trigger, then you're going to have to buffer those events, and they're going to be quite large events. Or you can go again the full triggerless route, but then you're going to have to swallow this huge bandwidth. And then finally, I just wanted to point out that there is a world beyond colliders. Smaller experiments now are looking to use hardware tracking capabilities as well. I give an example here of Mu1E. You can read about that experiment through the link. And so that's what I thought to share. I hope you can still hear me.
Yeah, we can. Can you hear us?
Yes.
Okay, good. So thank you very much. We have time for a few quick questions, and then there's more discussion time built in later in the schedule as well overall. I see Sasha's hand raised remotely, so why don't we start with Sasha?
Thank you, Christian, for the nice talk. I have a comment on page 16, where you talked about doing data processing on detector. It's a good idea, but it has some trade-offs. Like, for example, the more processing we do on detector, the power consumption is going to happen on detector, and that's a challenge, especially for trackers. Also, your circuit is going to be larger, and so you'll have to deal with more single event upsets and things like that, and that's very expensive to handle. If you want to do triple mode redundancy or something like that, it is difficult.
Yep. No, I completely agree. In fact, I tried to give that caveat twice in case it was missed the first time, because I think it's you can think of a lot of interesting things to potentially do at the front ends, but then I think as one starts to hit the design process, you start to realize that there's a myriad of trade-offs actually. So yeah, I agree with you.
And even when we look at the trigger systems and the latency of that, buffering detector is also very expensive because the memory has to be RAT tolerant.
Indeed, and it also goes in jumps, right? So you can't tune necessarily your buffer length to whatever you want it to be. It will also go in steps that might not correspond to what you want. So yes, it's not cheap.
Yeah, I have just one comment to page 17, and that just goes generically to training students, and it's partially the problem, I don't know, that some students come and they don't know even C++. They don't have a lot of coding experience, They learn C++ at some point and they learn root. But if you look at C++, the language itself is not really designed for highly parallel architectures like FPGAs. It's designed for state machines like CPUs, where things happen more or less sequentially. And I ideally would want to have some program in HAP that would allow students to learn about other things beyond C++. And it would be, effective or efficient, cost efficient to do that more centrally, like at some kind of schools or have classes at universities.
Yeah, I agree with you. I mean, I think the experience, I think we were pleasantly surprised, at least with the experience in CMS, as to how well HLS actually does. I think the initial thoughts was that it would just bloat your project in terms of resources. But surprisingly, it does okay. But I think we have to bear in mind that it's really meant as a prototyping tool and language, because exactly for the reasons, as you say, when you have to dig into the details, it obscures a lot of things that ultimately you might go back and fine tune or try to understand actually with RTL. I personally agree with you that I think having a centralized, more formal introduction to sort of hardware languages would be immensely useful. It might be always more efficient to maybe start with something like an HLS just to get going, to prototype an algorithm that you can run in software very quickly. But to really close the circle, I think it would be useful, extremely useful for our students to actually have a grounding, some sort of grounding in RTL.
Yeah.
Or HDL, excuse me.
Part of the issue with training is related to how funding is done, because we cannot easily resort to engineers to help with training students. Yes,
I agree.
Okay, unless there's a burning question, yeah, Darren has a.
Consistent in the comments and also in the slides about tracker design from Christian. In that, I think TDEC also has an intimate relationship with the detector design, at least for the heavy volume data, like trackers. Going to have this stubs forming coincidences or these concerns of power, bandwidth, and intelligence. I think there has to be this marriage between detector design and the TDEC if it should continue. I'm not sure we really emphasize it anywhere in our report.
Yeah, so apologies if people off mic couldn't hear that so well, but the main point was that this is an area in particular where design of trigger and data acquisition with the detector itself there's clear benefits and clear needs, and that's something that we should highlight in the report. Okay, so we are running a little behind schedule, which is okay for the overall session because we have a lot of discussion time built in. And now we are where we can have a coffee break and get coffee. So we will take a 15-minute coffee break. There's coffee in the Hub building and Kane Hall, which I'm pointing my hands, but I have no idea if those are actually the correct locations. And then we will reconvene here and have more discussions on tracking triggers in 15 minutes.
Okay, all right. Thank you all for the invitation. So we are on this general topic. A lot of what I'm thinking about is sort of exploratory. If in the discussion session, you will probably see how many things I'm assuming will somehow work out. So if you said this has to happen, this has to happen, this has to happen, and all of those things are not there at the moment, then anything I'm thinking about is probably useless. So, but the attitude I'm taking is, well, let's just look at one thing at a time, and if that works and it has some promise, then we can go figure out the next one. And if that works, then we'll go figure out the next one. And as I was just mentioning, like about the WMAS, no explicit time scale on this. We all know it's, let's say, sort of around the corner and the clock is ticking, but we'll see wherever this ends up. So on that note, here is sort of a motivational picture I had, which is, why can't I go back? Oh, you moved forward from that. Thank you. Okay. No. Go ahead. So this is a topic that sort of triggers in your mind some aspirations, which is, there's a lot of literature now. Even Hitoshi, I think, mentioned it in his summary from 2 days ago. that novel things like disappearing track type things, almost degenerate doublets like that, where a charged particle disappears to some neutral thing. Maybe this is a dark matter model, who knows? But this sort of thing is interesting. We should figure out how we can do it. So in the best of all worlds, I've used this as a thought-provoking thing. It's not like what I'm thinking about could not be done with the outer silicon. It could just as well be done with the outer silicon. But if all else were the same, what happened? Did I do something?
That's great.
Gotta get you. I'll get that.
Design functionality.
Oh, no, we lost our captioner.
Okay. Should, hopefully they'll reconnect to the, yeah,
Something's blinking here. That's a good sign, right?
yeah, so I think that's still working, so that's okay. Okay, maybe you can message somebody or. Thank you.
Keep going. Keep going. Okay. So if all else were the same, one might say, let's see if we can trigger on the pixels. So what I'll talk about is sort of specific to the pixels, but it doesn't have to be. Appropriate things can be changed. It could equally well work on the outer layers or both or whatever. So on that note, let's go forward. I'll show just a few slides on if you could trigger on tracks, then this is just pure geometry, right? You can see logarithms in terms of centimeters. So 10 centimeters is here and 100 centimeters is here. So if the lifetime of a particle is on the x-axis, you are just asking from the exponential decay with the boost factor and all of this times the proper lifetime, what fraction of the particles will get to 10 centimeters, 100 centimeters, 1000 millimeters, and so it's a lifetime thing. And if you were triggering on the muon detectors, you'd have to get out that far versus silicon strips versus silicon pixels. So you can sort of see just very naively, if you could, the closer to the detector you can trigger on the track, the more efficiency you get, and you become less dependent on the lifetime. So let's move forward. Okay, this is just a little more to quantify that. So this is sort of the transverse boost factor. And so this is a simple Rayleigh study that just says, as a function of different massive particles, say they're charged, and so they're produced by the Rayleigh process, then what is that transverse boost factor? So this is just gamma beta in some sense, and the logarithm of that. So you can see, of course, sometimes, you have enough phase space and enough parton density that you get high PT. Most of the time, they're also slow. So, of order 1, gamma beta tends to be for the bulk of the production of a pair of massive particles. Okay, let's go forward. So that sort of means that you don't want to rely on a big boost to get you out to the large radius. And so that's again motivating why you want to stay at inner radii if possible for track figuring. So this is now more explicitly the perpendicular component of gamma beta, and you can see the logarithm is peaking near 0. And it's almost independent of mass, light particles, heavy particles. A small dependence here, so the lighter you are, you do get a little more phase space out here. But the bulk of it is the distributions are roughly the same. Okay, let's go forward. Okay. So if you say relative to particles getting out to the muon triggers, so 100%, what is the additional efficiency you would get if you could trigger on the strips? So this is the strips. What is the additional efficiency you could get if you could trigger on the pixels? That's a higher curve. So if the C tau is very, very large, then they all get to the muon triggers anyway. So you don't need any of this. You'll just trigger on the muon system. But if they're shorter lived, then you start running out of efficiency in the muon triggers. Then these start helping. And the closer you can trigger on, as you see the pixels, the more you get. And of course, if you're too short-lived, then of course you can't get out there to any one of them. Even 5 centimeters is too much. So then you lose efficiency all around. The point being that regardless of what this heavy particle mass is, because the boost factor is typically invariant or very little dependent on that, these curves are scans from 100 to 900 GeV in the mass of the pair produced particle that you're looking at. And that doesn't seem to matter very much. So that's in some sense a bad thing, in some sense a good thing. Okay, let's go forward. So this is just quantifying that depending on the mass of the Rayleigh production. If you take some random model, so here's some model, maybe it's a good model, that the lifetime is 6 centimeters. So that's this dotted line on the C tau axis. Then comparing the two curves, you ask what is the signal yield? 1000 events will always be the upper curve and 100 events is the lower curve. Then how many events would you get for a C tau 6 centimeters if you could trigger on silicon pixels, those are those curves. If you could trigger on the strips, you could those curves, and if you trigger on the muon detector, it could be those curves. So it's saying for that kind of theta, getting out that many events, only very low mass particles have the appropriate production cross section. But if you could trigger on the inner detectors, then for even pretty heavy particles, you have the rate if you could trigger on that. So let's go forward. All of this is motivation. Then, of course, there is the ISR trigger. So you say, why do we need any of this? You could just trigger on the ISR, which is what is done now. And you can see what kind of efficiency cut or this acceptance cut that is giving you. So this is some QCD calculation that says the amount of ISR as a function of the heavy particle mass. As the particles get heavy, just from the nature of QCD, you get more ISR, so the efficiency goes up. But you see the numbers on the x-axis. For light particles, it's only 1%, getting up to 10%. So it's that efficiency loss that you're trying to get back in some sense by able to trigger on the charged particles directly. Okay, let's go forward. I think we've talked enough about this. Let's keep going. More what? Okay.